郭杰老师，请准备。Please get ready. 5, 4, 3, 2, 1. We are live.
Good evening, everyone. So thanks for your hard work in working on the Common Contest 1 at the ICPC training camp powered by Huawei. So we have the problem contributors listed in this page, and I will explain the problem statement and the brief outline of the analysis in the following slides. Okay, so problem 1 is a final exam. So the statement is not difficult to understand, but I will go through the outline sketch of the solution so that we will find that it may take some time to work on this problem. So it may not be a suitable problem as the problem A, but let's see the details. So in this problem, we would like to allocate n minutes. M is a real number to prepare for n exams. And then we have an equation to evaluate the points that when we allocate t minutes in the ith exam. And we want to maximize the total points for the n equations, for the n exams. So that is, we maximize the total sum of this function, and subject to the total time allocated is m, and then the time allocated is non-negative, and there's a range for this input settings, and then there's a one number we should pay attention to is that at most 18 exams have the coefficient AI greater than 0. So this problem, if you find out that we need to solve this optimization problem, then we know that there should be some property to analysis. So in a rough thinking, so the function fi seems not concave. So if this is a concave, then it's easy to solve. But it's piecewise projecting. And more difficult is that some AI are greater than 0 and some are less than 0. So they grow in different directions. And then the key idea for this problem is to do some analysis on the property of this fi and the property how we can get the maximal score for each exam. So here we have too much details, but you only need to take attention to the brief property of these equations. So we assume K is the number of exams with a positive coefficient for the quadratic term, and then we can derive a few property for this function. For example, so you can ignore the details, but you can ask the problem setters to get the detailed problem analysis. But here in this analysis session, I will just briefly go through the lemma, but you do not need to look at the details. So for example, we can derive, to simplify the problem, we can derive that the FIT can be written in this way. So we can move the CI out of the min and max functions. And then we can define some properties to help us to analyze the equations. For example, we can define the full score. There's a concept that how many minutes we need to allocate to each exam. For example, let's assume we have unlimited time. Then we can get the upper bound, a tight upper bound for the points we get, so that we will know the how many more minutes we need to spend on the exam. And after we exceed that number of minutes is no use. So we can define this concept to help us to analyze this. And then in the following, we analyze more properties, like if we spend X minutes in the exam, we spend non-negative minutes in the exam, then we always have a positive weak row. And then if there are only exams with AI greater than 0, then there's always an optimal solution with at most one exam that she spends time but does not get a full score. And there are some proofs, but you do not need to look at details because the tests are so small. But I will show you a few outlines. So for example, this number 4, to analyze the property when we have 2 exams, and then we spend S minute on both exams and what we get. And then we can also analyze that at the optimal solution for all the exams, she spends time but do not get a full score. Then we have this property. They have the same coefficient AI and BI, so that we can get the corollary. So there are a few more. So for example, if there are n quadratic function and we have the piecewise quadratic functions, and we perform a max out of that. So we have all these properties analysis, and after that we can solve k different problem. K is the number of exams with the coefficient AI greater than 0. So we see the limit, the maximum value of exams with the AI greater than 0 is 18. So the k is not that great. So we can analyze when we solve k different problem, how much time we spend to solve the problem. So the key idea for problem A is to analyze the property on the objective function, because it's a piecewise quadratic function. And then we analyze how we can simplify function. And then when we have only 2 exams, what happened, and then so on and so forth. So this is the basic idea of problem A. So it may take some time to analyze all the details. So if you're interested, you can work on this problem afterwards. So this is problem A. And then let's look at problem B. So problem B should be easier than problem A. Problem B is, the title is Travel Around China. And then the statement we can simplify as on this slide. So we have cities and expressways. They form a n by m grid graph with the cost on the nodes. And then we would like to compute the all pairs distance on this graph. And pay attention that the graph is very special. One is that it's a grid graph. And second is that it only has 3 rows, but it may have a very long, many columns. It has many columns. So it's a very special graph. And we would like to compute the pairwise, the sum of pairwise distance. And then for this problem, because it's very special and it equals 3, so it's straightforward to consider a simpler case. So it may be very straightforward that when we consider simpler case when n equals 0, by n equal to 2. And in this case, we can use divide and conquer to solve this case. So we can derive the property that the shortest path will stay inside the bounding box because it only has 2 rows. And then we would like to compute the all pairs distance of 2 rows. So for any path from one endpoint to the other endpoints, the shortest path will always go inside this bounding box. So this is a property. So because of this property, we can use a divide and conquer. For example, we count the sum of shortest path on the left-hand side, on the right-hand side, and in between, we enumerate the 2 cases, whether we pass through the point on the top or on the bottom. So this is the simpler case when n equals to 2. And can we extend the idea for the case n equals 3? the sample input tells us that a detour may be needed. So I forgot in detail what's in the sample, but as far as I can remember, we have the cost 1 on the edges, and we have a cost 100 in the middle. So that means if we go from this edge, this node to this node, so the path may not lie within this bounding box. So let's assume this is also 100. So we may need to do a detour for shortest path. So the sample input tells us that a detour may be needed, but we still want to use a divide and conquer like approach for this case. So in this case, the shortest path is not necessarily stay in the bounding box, in this bounding box, but we can still use the same idea, So we can still use the bit to divide the problem and merge 3 cases. But one special thing different from the case when n equals 2 is that we need to compute compute these 2 quantity using the shortest path algorithm for the detours. So on the boundaries, we may go outside the bounding box. So we need to compute the shortest path from here to here or from here to here, so that we can still use the divide and conquer idea to solve this problem. And the overall time complexity is m times log m squared. Okay, so this is problem B. Let's see problem C. So problem C probably is the easiest problem in this contest. So problem C, the title is wandering. So I can see many teams have solved this problem. And the statement is that starting from the original point, we perform a walk in n random steps. And in each step, we walk in this direction, and this direction is drawn uniformly inside a circle. So for each step, we have a different radius, but we draw inside this circle randomly and use that vector as our step. And then we walk in the next step. And after n steps, we move to this location. And because each step is draw randomly, so these xi and yi are random variables. And we would like to compute the expectation square of the expected distance to the origin. So this is the problem statement. And also the solution is also straightforward if you are familiar with the statistics and random processes. So we know that the xi, yi are random variables, and according to the property for the expectation operator, we can derive all these equations. And at the end, because of the independence between different random steps and because of the property for the expectation operator, so we can get this value. So the expectation of the xi and yi, xi squared plus yi squared is easy to do integration along the cycle. So we have a dr here, and then how much property when for this radius is the area inside this band. So so use the basic integration, we can get the expectation of that square of distance. So this is a problem C. And then the next problem, insects. So there are also many teams solve this problem. So it may not be straightforward to understand the problem, but after you get the rules of this game, it's not that difficult. So let's review the statement of this problem. And we have n insects in the field. Each has a type and a level. So we have n insects, and it has 2 properties. And initially, every insect has a C buff, so they are special insects. And the players can do multiple terms. Player can eliminate an insect and possibly add a new insect. And he can add the new insect if the eliminated insect has the C buff. So initially, the N insects have a C buff, but the newly added insect do not have a C buff. So when we eliminate an insect with the C buff, what we can do, so we can add a new insect with arbitrary type and the level L. So L is defined by the rule. L is defined by the rule. L is the highest level among the remaining insects with the same type as the eliminated one. And if no remaining insects have the same type, no new insects can be added. And the new insect does not have the C buff. So here's the rule. Here's the rule. And the question is ask you to compute the maximum sum of levels for all remaining insects in the field by eliminate at most k insects. At most k insects. So you need to compute 1, 2, so on, and k. So you can you need to compute a sequence of number of insects that we can eliminate at most. And the purpose is that for the remaining insects on the field, we need to maximize the sum of levels. And we have a rule here for the enumeration. So we can see that we would like to enumerate an insect with a higher level, but not necessarily the maximum level. Intuitively, we would like to remove insect with a higher level so that the new insect we added has a higher level so that it will increase the total sum, the sum of levels. So here's the problem statement, and let's see the solution. So for this problem, we also need to derive some property for the optimal case. And let's see what's the property for the optimal case. So in the optimal case, we can find two statements. One is that in the optimal case, every enumeration adds a new insect. Otherwise, because the problem asks us to compute the maximum sum of levels when we do at most k enumerations, so we can just ignore the enumeration if it does not add a new insect. So this is the first property. And the second is that in the optimal case, every new insect has the same level L, So how can we derive this property? For any optimal case, we can always construct another optimal one, so such that all new insects have the level L. So what's the L? If a new insect with the highest level L is added in the kth step, we can always construct another in other case that the level L insect is added at the first step. So L is the highest level in this enumeration process. And for the remaining enumerations, we set the type of the previous added insect as the type of the one to be eliminated. So if we expect the type for the next insect to be enumerated, so in the last step, we just add insect with level L and with the type as the one to be enumerated, so that for the next insects, we can also add another insect with level L. So these are the two properties for the optimal case. So after we analyze this problem is relatively easy to solve. Let's see, we have questions. Okay, there's one question for problem C. What's the C buff? So the C buff is just a property, and other property for the insect. So initially we have n insects. All of them, after we enumerate, you can add one. But for the added insects, it will not have the C buff. So when we enumerate insect without the C buff, we cannot add a new insect. So that's the C buff. And then yes, the courseware will be given. The courseware will be given. Okay. Oh, in reality, it's a game. It's a game. It's not a reality case. So it's like you're playing a video game. Okay. Yeah, and the algorithm, we enumerate the type for the enumeration at the first step, right? Because according to this property, so we know that every new inset has the same level L, but what L we should perform in the enumeration, we do not know yet, because it's not necessary the maximum at the beginning is the best, because we care about the increase of the levels, not the value of the levels. So we need to enumerate the type at the first step to determine what's the L. And then we add k new insets. The contribution to the sum of levels is a linear function of k. So there are some details omitted here, but after some careful derivation, you will find these, and you can use some data structure to find the optimal sequence for enumerating at most 1 to k insets in log n square time. So the overall time complexity is n times log n squared. So this is problem D. And problem E, I also see many teams solve problem E, minimum spanning tree. So a graph has n nodes and n edges, but we do not know the exact weights of the edges. We only know that the edge weights are a permutation of this set from 1 to m. And we also know that the minimum spanning tree consists of the first n-1 edges. So the graph is given in the input. So you will know what is the first n-1 edges. And we would like to find the number of edge weights permutations satisfy the condition above. So satisfy this condition. So we would like to count how many cases, how many permutation leads to a minimum spanning tree consists of the first n-1 edges. So here's the problem. Right. So at my first reading of the problem, we can find that it's a combinatorial counting problem. We need to count the number of permutations. But how to count? It's best to count smartly. So it's a combinatorial counting problem. And let's see what we can do to count smartly. So instead of enumerating all these configurations, that's the weights for the first n-1 edges. For the first n-1 edges is a combinatorial number. Instead of enumerating these many configurations, we only need to enumerate n the factorial of n-1. So that's the relative order for the first n-1 edges. So how about the weights for the non-tree edges? So we use the well-known cycle property to count the case of non-tree edges. So the cycle property is that for any cycle in the graph, an edge weight is larger than the others, then this edge cannot belong to a minimum spanning tree. So this is a cycle property. So if we would like to ensure that the first n-1 edges are on the minimum spanning tree, we have a relative ordering for the weights for the tree edges and non-tree edges. So for each non-tree edge, it must be larger than the largest edge on the tree path. And we can count it by using some combinatorial method. Then there's some implementation details. We can optimize the enumeration of the tree edge dynamic programming. So the overall time complexity is m times 2 to the n. So this is problem E. So it's a counting problem. And if we count smartly, you can solve it within the one-time limit. Okay, so this is problem E. Is there questions? Okay. Yeah, so as I said, we will share the problem analysis after how to count this DP. Yeah, so there's some details. So if you would like to discuss, I will also write down the content method of the problem setters. So there's some details. So I will only go through the overall idea. Okay. And then problem F flow. So let's see the problem statement. Given an undirected graph with edge weights for each vertex I. So in the problem statement there's a story, but we can just ignore story. But what it does is that for each vertex I, add an edge from this label to the next label modularly, and then the edge has a weight, a very large weight. So in fact, in the problem, it's not infinity, it's 10 to the 9, but it's big enough. And let Ci be the minimum cut between vertex I and vertex J. And we need to calculate the sum of Cij for all pairs of vertices. So the sum of cuts for all pair of vertices. And the N and M are in a medium scale, 20,000. So in this problem, we need to calculate the sum of cuts. Questions? Yeah, so that's the problem setter. So when we see when we need to calculate the sum of cuts for all pair of vertices, we think of this data structure. We think of this data structure, the Gormley-Hu tree. So this data structure is capable of computing all pair min cut in ON or 9 queries instead of n square queries. So it's all pair min cut. So it's a straightforward implementation is to just compute all the pairs. So because they are n square pairs, so we need to query the cut for n square time. That's a straightforward approach. And when we use this data structure, we can reduce the number of queries from n squared to ON. So the remaining issue is that how to compute Cij, how to quickly calculate Cij. That's the cut. And remember that the graph we perform the cut is a special graph because of the newly added the infinity edges. So it forms a circle. Assume we label the nodes in this way. So we have this very thick edges form a circle. So every min cut, it must cut the circle into 2 halves. So it's in other cases, if we cut more than 2 infinity edges, then the weight will be much higher. So every min cut must cut the cycle into 2 halves. So this also can easily derive from the property of this graph. Essentially, 2 infinity edges in Cij are cut. And let's see define another quantity to help us to calculate Cij. And we define Aij for the cost for cutting the wedge Ij from the rest. Hello? Can you hear me?
Yes.
Okay. Okay. Yeah, switch to another network. Thank you. Yeah, so we use the matrix Aij so that we can convert the computation of Cij to some operation on this matrix Aij. So how to do the computation? So initially we get an n by n array with initial value 0, and then we add the subrectangles. So to compute Cij, then we perform online queries, query the minimal subrectangles in the Aij. So Aij is a property I just mentioned. It cut the segment from I from the others. So we can just do a minimum query on Aij to get the min cut Cij. So you can work on the details. So in the implementation, we can use divide and conquer on the x-axis and use a segmentation tree to maintain the y-axis for more efficient implementation. So eventually it takes n log n square time and n log n square memory. So this is the basic idea. So of course there's some details for the implementation, but we can see the two basic idea. One is that we use the data structure, to reduce the number of queries, and then we construct this Aij matrix for the computation of Cij. And then because of the relation between Aij and Cij, we can use some efficient data structure for this task. So this is a problem F. And let's see this one. Problem G, revenue. So let's read the problem again. Let's see the problem again. So the seller sets a price in P. So P is a constant, is a given constant. Seller sets a price in P. And then buyer has a valuation profile. So it's a vector. So the pricing is just set some price for n items. And the valuation is how the buyer estimate how valuable this item is. And the utility to buy the ith item is the difference between these two terms. So when the prices gets higher, then the utility becomes smaller. And if the valuation gets higher, then the utility increases. So the buyer will purchase a single item with the maximal positive utility or buys nothing. If the utility is 0 or negative, then the buyer buys nothing. Otherwise, it will buy the one with the maximal positive utility. And if there's a tie, the buyer will buy the one with the lowest price. And seller knows that V is a random vector. So you can imagine that previously we only describe for one buyer. So let's assume there are many buyers. So they evaluate the items in different ways. So we can think about it as a random vector. So seller knows V is a random vector, and then he also knows that the VI follows a no marginal distribution Fi. So it's a discrete distribution. So Vi is one of the k values, and for the property of each value, we also know the probability. But the correlation among the VIs and the joint distribution are unknown. So the task is to have the seller to estimate the minimum expected revenue. So this is a problem statement, and the proof is quite complicated. But I will show the sketch of the solution, so that you may derive the details afterwards. So let's see the basic idea. The basic idea is that the joint distribution of the VI is unknown, and we need to estimate the minimum expected value. So how to get the minimum expected value? then we can construct a worst case joint distribution because it's unknown. And we need to find the minimum expected value from all possible joint distribution. So one way is to construct a worst case joint distribution. And to make the thing simpler, the worst case joint distribution is the one that all the valuations are perfectly coupled. So we have a formal definition, but here we just present it intuitively. So how is the perfectly coupled is that if we draw a single random variable uniformly from the range 0 to 1, it determines the whole valuation profile. So there's one intuitive explanation, but it's not formal. So our task is to construct a correlation to minimize the revenue. So to construct perfectly correlated valuation to minimize the revenue. And the basic idea is that so many items, right? And the buyer will buy the one with the biggest utility. So the idea is that we create a correlation that for the biggest utility, the buyers buys. In that case, we try to put as many possible as in that case for all the other items with a smaller utility, but with also with a greater price. So we would like the seller to sell at lowest price so that we can get the minimum expected revenue. So that's a basic idea. And of course, there's some proofs and constructions, but I will ignore those parts and show the sketch of the solution. So if we implement the solution is not that difficult, but of course, to derive the property is it will take some time. So we sort all the entities, so we get many pair of the valuation and properties, so we can expand for each item and each case. So we get all these pairs, and we sort them with the descendant utility. So so it forms a sequence. So we process this sequence one by one. For any previous length k of this sequence, we insert the kth entity in a mean price heap, in a heap, and then the top of the heap is the one with the minimal price for the previous added entities. So we add these entities in this heap, and that SIK be the sum of probability of the ith item at length k, and TK is the maximum of this probability. So next thing we do is we get the entity from the top of the heap, and it consumes this amount of probability. Because we have one step, and then we may increase, or we may stay in the previous probability. But if there's some extra non-negative probability we add, we can look at the top of the heap, and then we reduce this amount of probability for that entity. And if all the probability for that case are already consumed, then we pop it from the heap. So it's guaranteed that we can construct a legal correlation with this item having the maximal utility at the current case. So although it's a deterministic algorithm, but in case we are constructing the correlations in the joint distribution. So we follow this algorithm until TK equals 1. So this is the sketch of the algorithm, but of course we skip something in between. So previously we have a basic idea to construct a worst case joint distribution, and here's an overview how we construct that. But there's some details behind. Why it can guarantee a legal correlation. But this is the basic idea. The basic idea is to construct the worst case joint distribution such that every time we buy is at lowest price. So that's the basic idea, and we need to guarantee that in that case, it is the maximum utility. So these are the conditions to consider in this problem, problem G. And then let's see the next problem, problem H. So it looks like another data structure problem. So in this problem, we are given an array A of length n, and we can do this query to find the longest loose segment in A. So how to define a loose segment? So it means that the minimum value in this segment plus the maximum value in this segment is greater than the length of the segment. So if we specify this property, we call it a loose segment. And then we may have multiple operations on this array. So we change the array in m turns, and in each turn we perform k pairs of element swaps. And then after these k pairs of swaps, we perform a query on the resultant A to find out the length of the longest loose segment. So at the beginning, we need to compute the length of the longest loose segment in A at the beginning. And after each turn, we also perform one more query. So according to the size of this problem, so we require a linear time of the queries. So let's see the idea to solve this problem. So the tool we use is the Cartesian tree. And Cartesian tree is capable of maintaining a list. So for the nodes in the Cartesian tree, it has two properties, index and weights. And we perform an in-order traversal of this tree. It gives the node list with the ordered indexes. And the weights in this tree, in this type of tree, satisfy the heap property. So it's a data structure can help us to maintain these two relations, the indexes and weights. So given this data structure, if we know this kind of data structure is capable for maintaining these two quantities, then we can construct a Cartesian tree to solve our problem. For each subtree, we maintain three quantities. One is the length of the longest loose segment. That's the how we want to what we want to compute, and the size of the subtree, and also the maximum value in this subtree. And the basic idea to implement the queries efficiently is to perform a dynamic programming on this tree. And in the following are a sketch of this algorithm. So we merge the information to list A and B. So this is a lowercase a, this is a subtree A, and this is a subtree B. So according to the property of the Cartesian tree, it's guaranteed that A is smaller than the minimum of the left subtree and the right subtree. So in this Cartesian tree, we use this property as the weight. And then there are multiple cases. So assume the max is the maximum value of the left subtree is smaller than the maximum value in the right subtree. So here's the case for the following analysis. If this is the opposite, we can derive similarly. So if the maximum value of the right subtree is greater, then we may try to get a longer one. So this property, this condition is get from the definition of the loose segment. So if you remember, loose segment is that the length smaller than the min plus max. So because of this property, A is smaller than this. So A is the mean. A is the mean. And then B is the max. So if we merge these two, so B length plus 1, B length plus 1 is the length of the list after we add A to the right segment. So if we satisfy this property, then A and the B subtree forms a loose segment. So this is a possibility to form a loose segment, and then we extend to the left to compute the longest loose segment. So this is the answer. So this is the case. And for the other case, if A plus the right subtree does not form a loose segment, then the answer is the longest loose segment from the left subtree or the right subtree, and the proof are omitted. So this is the basic idea for the dynamic programming. But here we use the data structure of the Cartesian tree for us to maintain these values and perform an efficient query for this value. So this is a problem H. Okay, and then we have two more problems. So the remaining two problems are more on the properties of graph on the streams. So here problem I is a color. So let's review what's inside this problem. So we are given a complete graph with n vertices, and each edge has one of the m colors, and no two adjacent edges have the same color. So this maybe I added by mistake. So I'm not sure whether the text case has this restriction, but probably it's not. Sorry. I made a mistake. Sorry. This is the case for the legal coloring. This is a case for the legal coloring, but not the case for the input data. Okay. So we would like to color so that each edge is one of the m colors. Questions? Okay. Yeah. So so a legal color is that no adjacent edges have the same color, and we need to check whether we can extend a given complete graph to another complete graph with more edges. And because we only have m colors, so the maximal complete graph only has m plus 1 edges. And here, one minor details you should pay attention to is that for the input complete graph, it may not be have a legal coloring. So this is a problem for a coloring. So the programming is not that difficult, but if you need to derive all the properties, it may take some time. How to do some modeling to derive the properties. So we have some easy case. For example, what I mentioned is that the initial graph contains two adjacent edges with the same color. Then we can directly print no. And then if m is a even number, that is the eventual complete graph has an odd number, then you can also print no, because in that case you cannot find an assignment for the no adjacent edges have the same color. And in other cases, now we have M family of sets. So it defined by the coloring. So each color, so we have M colors, each color defines a family of sets. So when two vertices connected by the same edge, they are in the same set. Right? So each family contains this many sets, and each set contains 0, 1, or 2 vertices. So we denote as 0 set, 1 set, or 2 set, right? So we do this modeling so that from the coloring, we can have a M family of sets. And with the first M points given, we can add 1 to M to N vertices into the sets. So if here are some family contains greater than these many sets, then we can also output no. So otherwise, we can just print the answer yes. So if we perform a check-in to check whether the is possible or not, then we can stop here. And in other cases, if we also need to provide the coloring solution, then we can do the following things. So to show that we can add n-1 vertices. So consider we already have these many 2 sets, and we need to add more. Right. So at the beginning we have n vertices, and we need to add to n-1. Yeah, so it seems some discussion. Okay. Yeah, so so these 2 numbers are from the cases that at the beginning we have n vertices, and at the end we need to maintain this many M colors. It's M colors. Yeah, so to get the solution for the coloring of the next vertex. So let's see how we can construct. We can construct network flow as follows. Yeah, so as said in the checkbox, there are many ways to solve it. So this is only one possibility. So we can construct a network flow as the following, so that we can find out the coloring for the edges. So so we can construct a bipartite graph with a source S and a sink T, and then this bipartite graph consists of two kinds of nodes. On the left-hand side, it represents a family. So the family means the colors. On the left-hand side is the colors. So colors defines the families of the sets. And on the right-hand side, it represents the 0 set and 1 set that we already have. So intuitively, on the right-hand side is the nodes that we need to find out the coloring. So given each family an edge SA with we set the capacity 1, and for each 1 set is the edge to the sink. We also keep it as a capacity 1, and give the 0 set and add to the sink with a capacity M-M. So if a family A contains 1 set or 0 set, we draw an edge from capital A to lowercase a with capacity 1. So we can construct a maximum flow by giving each edge in A. So after solving this network flow, because the property for the network, we can have a integer maximum flow, and then we can use the edges to find out the assignment. So we have on the left-hand side, these are the color, and on the right-hand side, on the right hand side. So it's the vertices. So in this way, we can find out the vertices plus one 0 zero set. So in this way, we can find out the coloring of the edges after we perform a network flow on this graph. So we can find out that if there exists a legal solution, we can always find out the coloring. So this is one possible solution to problem I. Okay, so the last one. So probably there's some data we need to check. We need to check for this problem afterwards to see whether there's some mistakes. But here, because the problem statement is relatively difficult to read, so here I will help everyone to read the problem again. So I simplify the statement into these slides. So the problem J, horses. So there are M horses in a QA. So to make it easier to understand, so we call it a string. Because we have horses, and to represent the horses, we only use the type of the subspecies of the horse as its name. So we do not have M labels, we only have N labels. And there are N subspecies of horses, so we call a horse a character. So that the Q is a string, and one horse is one character. And some horses are friend subspecies. So if two adjacent horses in the queue belong to friend subspecies, they may swap in the queue. So that so because we call a queue a string, so that means that if the characters satisfy some have some relation, we can swap adjacent characters. And then because we can perform swapping, then we can define the equivalence. We use this symbol to represent the equivalence. So what are two equivalent strings? If one string can be generated from the other one by the legal swapping. So what is a legal swapping? There's some characters we define. There's some friend characters, so that we can swap the locations if they are adjacent and if they are friend. And if we can generate one string from another by these legal swaps, we call these strings equivalent. And the problem statement is relatively difficult to read, but the basic idea is to find the minimal commuter B of string A. So what do we mean by the commuter? So if this string BA is equivalent to string AB, so we call B is a commuter. And then the minimum means that so the B cannot be decomposed into smaller substrings. So if B can be decomposed and the C and D are also commuters, then B is not minimal, right? Because we can always do this because B equals CD. So for CDA, we can convert it to CAD and then ACD. So because B is not minimum, if B can be decomposed, then we do not need to count these B's. So B cannot be decomposed into CD such that both C and D are commuters. So this is one meaning of minimum. And the other meaning of minimum is that B is lexicographically the least. And our problem is to count the minimum commuter B of string A. So this is the problem statement. The problem statement. Yeah. So because there's a long discussion for the details. So here I only present the sketch, how to solve this problem. So there are two kinds of minimum commuters of A. So the one case is that a character can swap with all characters in A. So this is the first case of the minimum. So it consists only one character, but according to the friend, we can swap with all characters in A. So of course, this single character is one of the minimum commuters. So we can simply count these cases. And the second case is that ignore the characters not in A. We only consider characters A. The string consists of a single kinetic component in the complement of the frame graph. Then this is the case A. So we have a frame graph. The frame graph means that if there's some adjacent character, we can, and if they are friend, we can swap it. And the complement of frame graph is that we cannot swap. We are forbidden to swap. And then if a string consists of a single kinetic component in the complement of the frame graph, so that means that the strings consist of characters, the characters that cannot be swapped. And we may assume the characters in A are connected in the complement graph. So that means we also assume the characters in A can also not able to swap. Otherwise, we will do more effort to derive the actual cases. But here we only consider the simpler cases that characters in A are connected in the complement graph. And in other cases, we can convert to these simpler cases. And then we show that if this is the case, if A and B commutes, the shorter one can be a prefix of the longer one. And by induction, we can prove that they are the repeated of the same substring. They are repeated strings of the same substring. And so in this case too, we only need to calculate minimum C. So in this case, we need to pay attention that for the string, for the equivalent strings, it's not necessary to get one from the other by swaps. So here's an example. If A equals 1, 2, 1, 2, and 1 and 2 are not friends, 1 and 2 are not friends, and B is this pattern. So we also have the property that AB equals BA. We do not need to do any swap. So this case is it also satisfies the property for equivalence. Right, one can be generated from the other by legal swap. So we can perform 0 swaps to get BA from AB. So this is also the case. So this case is what we mentioned in here. So it's the case that we do not perform swaps because A consists of all the characters cannot be swapped, and also B also consists of all the characters cannot be swapped. So this is the only case that AB equals to AB. So by induction, we can find out that both A and B, if they commute, so they are the repeated of a pattern C. So A is a pattern C repeated by I times, and B is a pattern C repeated by J times. And so in this case, we need to calculate the minimum C. So to find out the cycle. So we in the following are some details. So cyclically, we move the biggest character to 1 and calculate the minimum representation by topological sort. And then we cyclically move the biggest character to the front again and calculate the minimum representation by topological sort, and then we use KMP algorithm to calculate the minimum P area. So these are the ways to the string operation. And at last, we move C prime cyclically back to get C. So here's the case 2. So and here is an example of case 2. Of course, after the problem analysis, we will communicate with the principal camp and also the index whether how we can share the problem online, and then you can also practice more to solve remaining problems. Okay, so it seems the problem setters already solve a lot of problems, and that's all of the problem analysis. And thank you for listening.